Hello everyone, welcome to the solution of LeetCode problem 746 named minimum cost climbing stairs. In this problem, we are given an integer array named cost, where cost of I is the cost of ith step on the staircase, and by paying the cost, I can jump whether one step or two steps from this staircase. And we can start this jumping either from index 0 or from index 1. Now, we have to tell that what is the minimum cost to reach the top of the floor. There are some example given, but I want to explain the solution and the thought process by using one of my custom example, and let's see what we can do. In this example, we are given three values in a vector, which is 5, 10, and 15, and we have to reach to the last position, which is position 3, and we can start jumping from either position 0 or position 1. And in each step, we can jump one step or we can jump two steps after paying the cost. Suppose from position 0, we can jump one step and reach position 1 by paying cost 5. And we can jump two steps and reach position 2 by paying cost 5 as well. And we can start jumping from position 1 as well. So we have to tell what is the minimum cost to reach into the final position by using this mechanism. At first, I hope you understood the problem, and let us find the problem category. In this problem, in each step, we have two decisions to make. Either we can jump one step or we can jump two steps. And when we have this kind of decision to make, sometimes we solve this problem by using greedy algorithms. But can we apply a greedy algorithm in this situation or in this example? Let us try to figure it out. Suppose we are given an array which has many values, and one of the value is 1000, and we have many other values as well after this. By applying greedy algorithm, we can jump two steps consistently, because jumping two steps is much optimal than jumping one step twice. It is the fundamental observation of the greedy algorithm. So if we want to apply greedy algorithm in this situation, we have to jump two steps consistently. And it is possible that if we make two jump consistently, we can somehow reach into a cell where the cost associated with this cell can be very high, but the cost associated with other cell can be very low. Suppose in this case, the cost of each cell is 1 except this. So here it is optimal not to jump two steps consistently, because if we jump two steps consistently, we can reach into the cell where the cost is very high. So it is said that we cannot use greedy algorithm in this situation. Now let us try to figure it out, what kind of solution we can make. Let's try to figure it out whether we can solve this problem by using a decision tree or not. In each step, here we have two decisions to make. Either I can jump one step or I can jump two steps. And we can start jumping from either position 0 or from position 1 as well. So suppose this is our start point, and we can start our journey from position 0 or from position 1. Now, suppose we are in the position 0, and by jumping one step, we can reach position 1, and by jumping two steps, we can reach position 2. And the cost associated with this jump is 5. And from position 1, by applying one jump, we can reach position 2, and by applying two jump, we can reach position 3. And the cost associated with this jump is 10, which is here. And from position 2, we can use one jump and reach position 3, and we can use two jump and reach position 4. And the cost of this path is 15. And we have reached 3 in one way, and we have reached 4. But we cannot reach 4, because if we go 4, we will become out of bound. So we cannot explore this kind of solution. Anyways, from position 2, we can reach position 3 by using one jump, or we can reach position 4 by using 2 jump. And the cost associated with this jump is 15. And from position 1, we can reach position 2 by using 1 jump, and we can reach position 3 by using 2 jump, and the cost is 10. And from position 2, we can jump 1 step and reach position 3, and we can jump 2 step and reach position 4, and the cost associated with this jump is 15. So here we can see that from a starting position, we can reach position 3 in 5 ways, which is one of this, another is this, another is this, and another is this, and another is this. And the total cost associated with this path is 10, and the total cost associated with this path is 10 plus 15, which is 25, and total cost associated with this path is 5 plus 15, which is 20, and total cost associated with this fourth path is 5 plus 10, which is 15, and finally the total cost of this longest path is 15 plus 10 plus 5, which is 30. And here we can see that the minimum of the value among all of these is 10. So in this case, the answer is 10. Or we can say that if we start jumping from position 2 or index 1 by using jumping 2 step directly, we can reach position 3, and the cost is only 10, and it is the minimum among all of the values. So here we can see that the optimal answer is 10. Now, in this solution, in each step, we have 2 decisions to make, and if we use trivial DFS solution, the time complexity will become roughly big O of 2 to the power n, which is the exponential time complexity. Here, n is the height of this tree, or we can say that n is the length of the given array. But this kind of exponential time complexity is very expensive in terms of competitive programming. So we have to reduce this time complexity, or we have to find a way to reduce this kind of time complexity. And now let us try to understand how can we make this exponential time complexity into the polynomial time complexity, which is roughly big O of n. In this tree, we can see that there are lots of repetitive work. At first, we are in the starting position. From here, we can play the game either from a starting position 0 or from a starting position 1. Suppose we are in the position 0 right now, and our problem is what is the minimal cost to reach position 3 from position 0. And if we apply jump 1, we can reach position 1. And now our problem is what is the minimal cost to reach position 3 from position 1. Now from position 1, we can jump 1 step and reach 2. And now our problem is what is the minimal cost to reach position 3 from position 2. So here we can see that the actual problem is divided into lots of sub-problems. And from position 2, we know that by paying total price of 15, we can jump into the position 3. And this is the base condition. Now, we know what is the minimum cost to reach staircase 3 from staircase 2. So we don't have to explore this tree here, because if we reach in this tree, we have to check in what is the minimum cost to reach node 3 from node 2. But we have already calculated it here. So we can use the caching mechanism, or we can store the value into a vector and use this value here. From position 1, we know what is the minimum cost to reach position 3. So we have explored this subtree. And if we cache this value, and suppose we cached the answer somewhere. Now, if we reach this one, we have to check what is the minimum cost to reach position 3 from position 1. But we don't have to explore the graph once again because we have already did it here. So we can just use the value of this here. Now, if we explore the subtree presented in this one, we don't have to explore the subtree here. So we don't have to explore these nodes. Again, if we explore the subtree presented in node 2, we don't have to again explore the subtree here. So we don't have to explore node 3 and node 4 as well. Now, we have to explore only this part of the tree, and which is roughly big O of n, where n is the number of nodes. So we have clearly seen that we can reduce the exponential time complexity into the polynomial time complexity by using the caching mechanism. This kind of problem basically known as dynamic programming. If one problem has lots of subproblem and we can apply caching mechanism, then we can say that one particular problem can be solved by using dynamic programming. Now we have clearly understood that this problem basically belongs to dynamic programming category. Now let us understand this caching mechanism by using a graphical representation. Now, instead of going to the last position from the first position, we will try to solve this problem by going first position from the last position. At first, we are presented in the last position, and the value of reaching into the last position from this last position is 0. It is the by default case, or we can say that this is the base case. Now, we are in the position 2, and from position 2, by paying total cost of 15, we can jump one step and reach position 3. And by applying jump in the 2 step, we will go out of bound. So we cannot do this here. So from position 2, we can just jump one step and reach to position 3. So the value of this jump is the 15, which is already presented here. Now we are in the position 1, and from position 1, we can jump one step and reach position 2. Now our problem is, what is the minimal cost to reach position 3 from position 2? But we have already calculated it. So it is basically the caching mechanism. So we know by paying 15, we can reach position 3 from position 2. So we don't have to calculate it again. We can just use the cached value. So in this case, by using one jump, the total cost is 10 plus 15, which is 25. Now, it is also possible that from position 1, we can jump 2 steps directly and reach to position 3. In this case, the value will be 10 plus 0, which is 10. Now, the minimum cost to reach position 3 from position 1 is minimum of 25 and 10, which is 10. 10 already presented here, so we don't have to rewrite it. Now we are in the position 0, and from position 0, we can jump one step and reach position 1. But we know what is the minimal cost to reach position 3 from position 1, which is 10. So in this case, the cost of reaching from position 0 to position 3 is 5 plus 10, which is 15. And it is also possible that from position 0, we can jump 2 steps directly. By doing so, we can reach position 2. But we already know that what is the minimal cost to reach position 3 from position 2. So we don't have to calculate it. Basically, this is the advantage of the caching mechanism. We don't have to calculate the overlapping subproblems repeatedly. we basically have to calculate it once and store in the cache, and after that we will always use this cached value anyways. Now from position 0, by jumping 2 steps, we can reach position 2, and we already know what is the minimal cost to reach position 3 from position 2. So in this case, the cost will be 5 plus 15, which is 20. And the minimum cost to reach position 3 from position 0 is minimum of 15 and 20, which is 15. But 15 is not presented here, so we have to overwrite this value and insert 15 here. Now, according to the problem statement, we can start jumping from position 0 or from position 1. And we have clearly seen that the minimum of these two values is 10. So we can say that by start jumping from position 1, we can reach position 3 with the cost of 10, which is the minimum among the total cost of all of the possible ways to reach position 3. So here we can see that the answer is 10. Previously, we have analyzed why the answer is 10 by using the optimized decision tree. Now we have seen that the memorization technique and the actual calculation why the answer is 10, or why it is optimal to start jumping from position 1 and reach position 3 by only the total cost of 10. So this is the algorithm. Now let's move on to the code. At first, we are given a function named minimum cost climbing stairs, and the parameter of this function is a vector of cost. At first, we have to insert 0 into the last position of the vector, and after that, we have to run a for loop backwardly from cost of size minus 3 to 0, and each iteration we have to apply single jump or double jump, and by using double jump we can reach position I plus 2 from position I, and the cost of this double jump is cost of I plus cost of I plus 2, and by using single jump we can reach position I plus 1 from position I, and the cost of this single jump is cost of I plus cost of I plus 1. After that, we have to override the cost value with the minimum of double jump and the single jump. And finally, we have to return the minimum of cost of 0 and cost of 1, because we can start jumping either from position 0 or from position 1 according to the problem statement. Now, let us understand the time and the space complexity of this program. The time complexity of this program is big O of n, where n is the number of nodes or the size of the vector, and the space complexity of this program is also big O of n, because we have to take a cost vector or dp vector to store the values. Thank you everyone for watching these videos. We will get back soon with another LeetCode solution.